This will be the Chapter 14 lecture that I do for first year chemistry on the chapter called Chemical Periodicity. That's a fancy way of saying the trends in the periodic table. And in the last chapter we talked about the electron configuration notation, and I didn't mention about valence electrons, so I actually introduced that concept of valence electrons in this chapter. So these are the electrons that are in the outermost energy level or shell. So for example, if you're in the 1s shell, those would be the outermost, or if you're in the 2s or 3s or 4s, those would be the outermost electrons. And they're going to be s electrons or p electrons, so those are the only ones you need to worry about counting. And to count the valence electrons, the easiest way to do it, instead of writing out the electron configuration, is just look at the group A number. It's written on my periodic table from 1A all the way to 8A. We skip over the D block so you don't have to worry about them. So if you're in group 3A, you'll have 3 valence electrons. The only exception to this would be helium. It's over there in group 8 with all the other noble gases, but it only has 2 electrons, and they're both in the outermost shell. It only has 1 shell, so they're in the 1s orbital, and there's 2 arrows if you were to draw out the configuration. And so it has 2 valence electrons. So for example, if you look at calcium on the periodic table, it's found in group 2A. Those would be 4s electrons. It has 2 4s electrons, so those would be the ones that are furthest from the nucleus. If you look at nitrogen, it has a configuration of 1s2, 2s2, and 2p3, and the 2s and the 2p electrons would total 5. And so that's why it has 5 valence electrons. And argon is a noble gas, and so it's at the end of the row. It's group 8A, and it has 8 valence electrons. Those happen to be the ones that are at the third energy level. They are the 3s electrons and the 3p electrons, for a grand total of 8. The D and F block we don't worry about too much, but if you're ever asked how many valence electrons they have, we just said that they have 2, which are the s electrons. On the next page, we have the way to represent those valence electrons, or those outer shell electrons. Instead of doing arrows, they're actually represented with dots. So sometimes this is called the electron dot notation, or it's named after a dead white guy named Lewis, so it's called the Lewis dot notation. But the way the electrons are located around the symbol kind of changes from one class to another. You might have a teacher teach you a different way of putting the electrons around the symbol, but basically what I do is I tell my students to put the first 2 electrons on the right side, which represents the s electrons that are paired up, and then you could spread out the remaining 6 electrons, which kind of represent the p electrons. So you basically have 2 electrons on each side for a grand total of 8. Now there are some freak exceptions to this. Maximum number of electrons that you can put around the symbol is 8, but we don't worry about that in first year chemistry, only in AP chemistry. So let's take a look at an example. Nitrogen we know is in group 5, as I mentioned before, so you draw the 5 dots around it. And then hydrogen has only 1 valence electron because it's in group 1. Now there's an important exception. There's an important exception when you're doing the dots. For carbon, the valence electrons, we actually spread them out evenly, 1 on each side. So the students kind of freak out about that, but they can get used to exceptions to rules, and so this shouldn't be a big deal. Later on in a chapter when we start talking about covalent bonds, we explain why carbon has 4 valence dots spread out so it can make 4 covalent bonds. But I deal with bonding in a later chapter, but for now they just need to know what the dots look like. On the next page we start talking about the main meat of the chapter, which is the development of the periodic table and the parts of the periodic table, and then the trends in the periodic table. So we start with the person who developed the first periodic table, and it was Dmitri Mendeleev. I say he constructed the first periodic table. I'm sure there's some people before him that had it constructed, but he was probably the most famous Russian scientist who started arranging the elements in some sort of pattern. He left blank spaces for elements that were missing because he figured that not all the elements in the universe were discovered, and he arranged them according to their properties, just like we do today. But his properties, or his elements that are with similar properties, actually ran horizontally, and today we have our periodic table basically turned sideways, and so the similar properties are in the vertical columns, not like his, which are horizontal rows. And he was able to successfully and accurately predict the properties of missing elements based on the properties of the elements that were around the blank space. So if you're in the same row, he figured you had the same chemical properties and physical properties. So things like boiling point or density he was able to predict just from the elements that were in the same row, which would have similar trends in the periodic table. And another important thing about Mendeleev's periodic table is that he arranged them according to increasing atomic mass, which is the little decimal number underneath the symbol. Now, in 1913, Henry Moseley calculated a way to find the atomic number of an element, which is the number of protons, and then we rearranged our periodic table to go by atomic number instead of atomic mass. So some elements actually switched positions. The most famous elements that switched were tellurium number 52 and iodine number 53. If you arrange them by mass, iodine comes first and then tellurium comes second. But if you go by atomic number, tellurium is number 52 and iodine is number 53. So those elements are arranged by atomic number, not by increasing atomic mass. So the students have to know the basic differences between Mendeleev's periodic table and our modern periodic table, and they're mainly these. There aren't any blank spaces anymore. We arrange them by atomic number, not by increasing atomic mass, and our periodic table has similar properties in vertical columns, whereas Mendeleev's had them in horizontal rows. Now, what are the horizontal rows called on a periodic table? Well, they're actually called periods or a series, and the word series is printed on a periodic table. 4F is the horizontal row called the lanthanide series, and 5F is the horizontal row called the actinide series. So a series means that it's running across the periodic table. The vertical columns are called groups or families, and we'll specify specific names of these groups later. I like the term family because if you're in the same family, you sometimes have similar properties. Like in my family, we're a bunch of science teachers, so we have that similar characteristic. And so elements in the same groups or families will have similar properties, and we're talking about chemical and physical properties. Now we start talking about the big sections of the periodic table. The metals are located on the left side of a dark zigzag line that runs through the P block, and this also includes the F block. So the F block, the 4F and the 5F rows are also metals. All metals have shiny surfaces. They're malleable, which means you can pound them into a flat sheet. They're ductile, which means you can turn them into wire like copper wire, and they're also good conductors of heat and electricity. That's why we make pots and pans out of metals, because electricity can go through them. The nonmetals are on the opposite side of that zigzag line. They're on the right side, and the properties are the opposite as before. So instead of shiny, they're dull. Instead of being malleable, they're brittle, which means they break apart if you smack them with a hammer, and they're good insulators as opposed to being a good conductor. So an example would be sulfur, which is a yellow element. It's a very brittle solid, so if you smack it with a hammer, it's going to break apart. Another example would be carbon or graphite. Diamonds are made of carbon, and so if you smack a diamond with a hammer, it's going to shatter into a million pieces. It might be hard, which is a scratch test, but it's still brittle because it's a nonmetal. Now, metalloids are the ones that are on the border between the metals and the nonmetals, so they're basically sitting on that dark zigzag line. The only property you need to worry about metalloids is that they're semiconductors and they're used in making computer chips. Now, a semiconductor is a substance where if you put a small amount of voltage through it, it acts like an insulator, but if you get to a certain amount of voltage, it actually switches to a good conductor. So there's like a switch that clicks it from being an insulator to a conductor, and that's why they're used in computer chips. And the best example is silicon and germanium, Silicon Valley being the place where they have a lot of the computer chip manufacturers like IBM and stuff. The other parts of the periodic table that we talk about are the special name for the D block elements, and those are called the transition metals, and the F block elements are called the inner transition metals. Now, there was an old name called rare earth when I was in school. They used to call the F block the rare earth metals, but that's not used too much anymore because they're not really that rare. In group 1A, now we're doing the vertical groups, they're called the alkali metals, and they react with water to form bases. The special name for group 2 are called the alkaline earth metals, and they're used in they're used in batteries as the paste that the chemical reaction takes place in. They're alkaline batteries, and that's from an alkaline earth metal. Group 7 are called the halogens. They're the light bulbs that get super, super hot in overhead projectors. In group 8 are called the noble gases, and they don't form any compounds. They're inert. So you have to know those special names of the groups. On the next page, we start the trends in the periodic table, and the first trend is atomic size. So as you move down a group, you're going from 1s to 2s to 3s to 4s, so the size of the atoms are going to increase because the electron clouds are going to be larger and larger and larger. So you're adding more shells of electrons or more energy levels. And if you move across the periodic table, the size is generally going to decrease, and that's because you're adding more protons and electrons. You're adding more protons to the nucleus, and you're adding more electrons to the same distance from the nucleus. And so there's going to be a large positive charge increasing as you run across, and you're also increasing the negative charge. But this negative charge is at the same distance from the nucleus. So this is going to cause more attraction of the opposite charges, and it's going to pull the electron cloud inward. So as you go across the periodic table to the right, the elements actually get smaller. Then we talk about the definition of a cation and an anion, and we're going to compare the size of the atom to the size of an ion. Now, a cation is a positively charged atom, and how do you get positive charges in an atom? Well, you have to take away some of the negative charges. So if you take away an electron, you turn yourself into a cation, or you turn the element into a cation. And when you lose an electron, you're going to become smaller than the original atom, just like if you lose weight, you're going to be smaller. And metals are the ones that typically lose electrons to form the cations. The anions are negatively charged, and they're created by gaining electrons, and the anions are going to be larger than the original atom. So just like if you gain weight, you're going to be larger than before. If you gain an electron, the element or the anion would become larger than before. And the nonmetals on the right side of the periodic table are the ones that generally gain electrons. On the next page, there's a picture of the atoms gaining or losing electrons. On the left side, you see the lithium and sodium potassium atoms. They're getting larger as you go down a group, and as you take away one electron, they become smaller blue spheres. And then on the right side, you see fluorine, chlorine, and bromine. Again, if you go down the group, they're getting larger, but as you add one extra electron to fluorine, it gets bigger, and same for chlorine and bromine. So if you lose electrons, you're smaller. If you gain an electron, you're going to be larger. The next trend is called ionization energy, and that's the energy to remove the outermost electrons. So those are the valence electrons. So if you try to remove an electron from an element that's larger and larger and larger, it's actually easier. So as you move down a group, those larger and larger atoms have an easier time of losing an electron, so you don't have to smack them with as much energy. So down a group, the ionization energy decreases. It's easier to take away one of their electrons. So again, the reason is because these electrons are farther from the nucleus, so they're not as attracted to the nucleus, so they're easier to take away. So in general, larger atoms are less attracted to its electrons. And if you go across the periodic table, it's generally going to increase. That's because you're going from metals to nonmetals, and the nonmetals are trying to hold on to their electrons compared to the metals. Metals generally form cations, so they want to lose them anyway, so it won't take as much energy to take one away. And if you remember, as you go across the periodic table, the atoms are going to be getting smaller, and so if the atom's smaller, that electron that you're trying to remove is closer to the positive charge, and so it's going to be more attracted to the nucleus, so it's going to be harder to remove. Now, this word successive ionization energy just means you're trying to take away a second electron or a third electron from the atom. And if you remove more and more electrons, it's going to take more and more energy, because as you remove an electron, it's going to get smaller, and therefore the remaining electrons are closer to the nucleus and they're harder to remove. So the remaining electrons are more tightly bound to the nucleus. So taking away one electron might be, let's say, 20 joules of energy or whatever, but if you try to take away a second one, it might jump up to like 40, and if you take away a third, it might jump up to like 100. It depends on where that electron is located in the electron configuration, but generally the students just have to know if you take away more and more electrons, it's going to require more and more and more energy. Now, the electronegativity is the next trend, and it's a relative value from 0 to 4, 4 being the highest electronegativity on the periodic table, which is going to be the element fluorine, and it compares how much an atom is attracted to electrons in a chemical bond. So ionization energy is basically how much you're attracting your own electrons and you're trying to take one away. Electronegativity is how much the atom is attracted to another element's electrons when they're making a chemical bond. So for example, in the water molecule, hydrogen and oxygen make a chemical bond. How much is the hydrogen attracted to the electron pair that makes the bond, and how much is the oxygen attracted to the electron pair? And so here's the trend. As you go down a group, since the atoms get bigger and bigger and bigger when they make chemical bonds, it's going to be less attracted to those electrons. So the electronegativity value is going to be a smaller number. So this bonding electron is farther away from the nucleus, it's not as attracted. So again, it's basically the same trend as ionization energy. If you're big, you're less attracted. As you go across the periodic table, it's generally going to increase. Again, it's going to go to the highest value, which is fluorine. and the atoms are getting smaller, so they're more attracted to those bonding electrons. And as you go across the periodic table, you're going from metals to nonmetals, and nonmetals typically want to gain electrons anyway and form anions, so they're going to be more attracted or highly attracted to the electrons when they're trying to make that chemical bond. And you don't have to worry about the noble gases because they don't make compounds. We're not going to worry about that in first year chemistry. So fluorine is the biggest electronegativity at the top right corner, and francium is the smallest electronegativity at the bottom left corner. And the last thing we talk about is how many electrons an element gains or loses when they form an ion. And basically what the atom is trying to do is to become more stable. So it's going to try to look like a noble gas configuration. And so what you need to do is take a look at where the element is on the periodic table and look to see how far it needs to move to get to the noble gas that's closest to it. So for example, if you look at magnesium on the periodic table, it's number 12. The closest noble gas is number 10 in neon, so it needs to go back 2 places to get to that noble gas configuration. So magnesium will lose 2 electrons. If you look at iodine at number 53, it needs to gain 1 electron to get to number 54 and become more stable like the noble gas. So iodine will gain 1 electron to become more stable. And gallium will actually lose 3 electrons to become more stable. You can skip over the D block. You don't need to worry about losing those D electrons. So only your valence electrons are the ones you're going to remove. So gallium can be more stable if it loses 3 electrons. So boron is also in group 3, so it's also going to lose 3 electrons. So here's basically the pattern. If you're in group 1, 2, and 3, you lose 1, 2, and 3. And if you're in 5, 6, or 7, you gain 3, 2, or 1. Now you don't need to worry about elements in the D block or the F block because we're going to save that for AP Chemistry. And if you're in group 4, you actually could gain or lose 4, so we don't worry about gaining or losing 4 because typically those elements make covalent bonds and they share electrons instead of transferring them. So those are the Chapter 14 notes as fast as I can cover them. As always, this is just a quick review.